G'day, I'm James, and welcome to this bonus video on the beauty and the thinking behind matrices and vectors. In fact, I want to focus on the various transformations of the plane that come up in standard units on matrices and vectors, namely these 5 transformations: translations, rotations, reflections, dilations, also sometimes called enlargements, and shears. They often come up in the study, and the geometry behind them is actually a little bit tricky, and I thought it'd be good to talk about it a bit more deeply now to develop that intuition about the geometry of those 5 particular motions. So let me just go through them straight away. So we learned in primary school about the first 3, translations, rotations, and reflections, and most people are comfortable with most of those. For example, let's be very clear though. Here's my piece of paper. If I say, please translate that paper 3 units to the right and 1 unit up, I'll just shift this paper 3 units to the right and 1 unit up. That would be a translation. It's going 3, 1, up this way. So actually, if I show a vector of how I want to translate it, an arrow pointing this way, I guess you say the translation was like zoom, described by 3 to the east, 1 north. Great. And translations clearly are what's called a rigid motion. They keep the shapes the same. For example, I've got 4 corners here, all at 90 degrees. My image is again 4 corners, each at 90 degrees. It stays a rectangle. All the distance is the same. The distance between these 2 corners doesn't change on a translation. In fact, translations are rigid motion, keeps all distances between points the same, keeps all angles between line segments the same, keeps the size and shape of shapes the same. Translations preserve the structure of any particular figure in the plane. Zoom. Translation. Rotations, I think we're fine from primary school as well. For example, we're going to rotate this paper, say 90 degrees counterclockwise, about that dot in the middle. I'd get a transformation that looks like this. Zoom. Great. Again, it's preserved all distances between 2 points. If these 2 points are 8.5 inches apart, under rotation, zoom, those 2 matching points stay 8.5 inches apart. All 90 degree angles stay 90 degree angles, and so on. So rotation about a point is also a rigid motion, preserves the size and shape of various figures in the plane. And the final one, reflection, that we learn in primary school, is just take a line of an axis of sort of reflection. So I'll take, say, the vertical line and reflect it, and I'd get zoom, that. Or I could reflect about a horizontal line, I'd get, in this case, zoom, that. Or I could reflect about a diagonal line, it gets a bit weird, I get something like that in this case. So reflection again is another rigid motion. It doesn't actually change the distance between points. It doesn't actually change angles. In fact, it keeps the size and the shape of figures the same, but it does actually move them about on the plane. So translations, rotations, reflections, grand. They're from primary school. But the other 2 that seem to cause some trouble in high school mathematics are these: enlargements and shears. So I want to talk about those next, and also talk about their matrix representations. We did both of those matrices in the last video, but let me get the geometry a bit more going for our intuitive feel for them. So I need to get a bit more space on the board, so let me be back in a moment. Okay, I think I have enough room on the board to get this graph in entirety. All right, so we've just done translations, rotations, and reflections, at least a little example of their geometry. But let me now talk about dilations, also called enlargements. So here's a typical curriculum textbook way of presenting dilations, enlargements. Here's a figure, a little triangle. Suppose I want to create an enlargement by a factor of, say, 3. Enlargement with scale factor 3. Now, briefly in the last video, we said what an enlargement does, it pushes all the points on the plane away from the origin by a factor of 3. Now, what do I mean by that? For example, right now, this point is this distance away from the origin, so we're going to now move it 3 times that amount away from the origin. 1, 2, 3, it'll end up there. So this point here ends up here. This point over yonder is this distance from the origin. Now we'll move 3 times as far. That distance again, and that distance again, I think puts it there. And finally, this point, which is, I guess it's overlapping, that distance from the origin will now move 3 times away, that far away from the origin. Once, twice, thrice, puts it up there. So it looks like this triangle has now been shifted to this position on the plane, and look, it really has enlarged by a scale factor of 3. So this is a dilation or an enlargement with factor 3. That's it. So if you recall, a dilation, an enlargement, just pushes points away from the origin. All the points over here will get pushed away from the origin that way. Points this way will get pushed that way. Points over here will get pushed that way, just radially outward from the origin. Now, the word enlargement is actually a little bit misleading, because I did a large scale factor, it pushed things away. But if I did a scale factor, like there's a fraction like a scale factor of a half, it actually pushes things towards the origin. That's the confusing part. So I think many curricula go with the word dilation that doesn't say enlarge. That makes you think it must get larger, because it can get smaller. For example, let's do a dilation with scale factor 1/2. Very first point, this far away from the origin now becomes half as far from the origin, goes there. This point from the origin now goes half as far, which I believe is about there. This point from the origin goes half as far, which is about there. In which case, I have a feeling under a scale factor of 1/2, we actually get a smaller figure. Scale factor 1/2. All right, so that's why some curriculum don't go with the word enlargement, because it can actually, under an enlargement, get smaller. All right, so big scale factor gets bigger, smaller scale factor less than 1 gets smaller, or less than 1. What if I go for a negative scale factor? Suppose I did a scale factor, say, -2. Now that's interesting. What would that mean? So here's my original figure. It's this green triangle here, remember? So I did a scale factor of -2. It means, okay, this first point here was originally that distance away from the origin. Now I want to go -2 as far as away from the origin. Well, to go -2 as far as away means -2, go the opposite direction twice as far. So this distance once, but twice in the opposite direction, once, twice, gets me there. -2 far away is over here, there. This one, -2 far away, so I'm this far away this direction, but we'll go -2 as far, once, twice in the opposite direction, gets me there. And this one, -2 as far, once, twice, gets me there in the opposite direction. So at a scale factor of -2, yes, the figures become bigger, but in the opposite direction. So there's a scale factor of -2. So factor 3, factor 1/2, factor -2, that's what enlargements look like. That's what dilations look like. And if you recall, we actually did do the matrix for a dilation, and the way to see that quickly, look at the two fundamental points. The point, say, 1, 0. Where does 1, 0 go? Well, 1, 0 will go to, under a scale factor, let's say 3, it will go to 3 times as far from the origin. 1, 2, 3, it will put me there, to 3, 0. And where's the other fundamental point go? 0, 1. Under scale factor 3, it goes 3 far away from the origin. 1, 2, 3, up here, to the point 0, 3. That's what the two fundamental points go to. So you've just seen that as an enlargement under scale factor 3 is given by the matrix 3, 0, 0, 3. Bingo, which is what we did in the lecture previous. Great, so there's the intuition of an enlargement / dilation, and that's how you draw them on coordinate planes. I think many curricula want students to actually do this exercise, so it's a good thing I did it now. And there's the matrix representation for a dilation. Scale factor 3, 3, 3 on the diagonal. Half, half, half on the diagonal, -2, -2, -2 on the diagonal. Grand. All right, so dilations, grand. And now comes the tricky one, shears. So let's talk about those next, and now I definitely have to clean the board. I'll be right back. Okay, we've now talked about translations, rotations, reflections, and enlargements, dilations. Now comes the fifth one, shears. This often is not talked about in primary school. It's left to high school to talk about in some curricula. So if your curricula is talking about shears, I thought I should really dwell on shears to some degree right now. Now in the last lecture we did talk about them. We did actually get the matrix representation of a shear, but I really skimped over the geometry. So let's be really clear on the intuition of the geometry of what a shear is. Now I did talk about last time decks of cards and stacks of books and pushing them, so I thought it'd be good to actually take a stack of books and push them to demonstrate a shear. So here goes. So here's a stack of books. I think I've got 10 books. I'm going to push them sideways like this until it becomes a tilted stack of books. This stack of books has now just undergone a shear. Now this often happens in geology. For example, geologists have noticed that land masses can often get pushed side by sideways force, and what should be vertical now becomes diagonal. So geologists actually use the word shear to describe some motion of land masses. So here's a shear of a stack of a book. Let's see what actually happened. First of all, notice each book is the same height as it was before. Heights don't change. This book's at the top, stayed the same height. All that happened was it got pushed sideways. In fact, each book just got pushed sideways. So shears keep the heights of points the same. All it does is push points sideways. But the thing about a shear, yes, each book's the same height it was before, but each book moved a different amount. This bottom book didn't move at all. This book 1 unit up looks like it moved about 1 centimeter over. This book about 6 books up looks like it moved about 6 centimeters over. This book 10 books up moved about 10 centimeters over. So the amount each book moves depends on the height. The higher the book is, the more it moves over. The lower the book is, the less it moves over. So the amount of motion to the right depends on the height of the point. So that's the issue of a shear. All points stay the same, but each point shifts to the right by a different amount in proportion to their height. Very confusing. In fact, you can kind of see that there is sort of similar triangles going on. If I did imagine a triangle here, and I can see that, okay, the amount of shift over gives me one base for that triangle there, which would be in proportion to the base of that triangle there. So you actually see similar triangles going on, so you see the amount of shifting to the right is in proportion to all the other shifts to the right. So that's what people try to capture and when they try to write down shears mathematically. So now I need to go back to my graph paper and we'll do some examples with shears on graph paper like I did with enlargements, because that often comes up in the curriculum problems as well. So I'll be back in a moment. Okay, let's practice applying shears to actual shapes drawn in the plane. Namely, here's a rectangle on some graph paper. Let's hit it with a shear given by a factor of 2. Now remember, shears are not going to change the points, the heights of the points. So these points at the top will stay somewhere on the top. These points on the bottom will stay somewhere on that line on the bottom. Middle points will stay in the middle and so forth. But all the points will shift to the right given by their height. Actually, their height modified by a factor of 2. So very clearly, very specifically, here's a point. This point is currently height 1. It's going to shift to the right, double that height. It's going to shift to the right 2 places. 1, 2, puts it there. This point's also height 1. It's going to shift to the right, given by twice its height. It's currently height 1. Double that means it shifts 2 to there. All right, so these 2 points go to there, and I guess all the matching points in the middle will match them as well. This point over here is height 1, 2, 3, 4. Height 4, it will shift to the right by a factor double that, height by 8. So it will shift 8 units to the right. 1, 2, 3, 4, 5, 6, 7, 8 to there. This point here is positioned at 2, but height is 4. It will shift double that, 8 units to the right. 1, 2, 3, 4, 5, 6, 7, 8. Aha! So these points here match to those 2 points there. Voila, voila. Let's try a middle point like this one. This is currently height 2, so it will shift double that to the right. 4, 1, 2, 3, 4. This one here is height 1, 2, 3. It will shift double that. 1, 2, 3, 4, 5, 6 to there. And in fact, you can see that the shear does this to this stack. Like I said, for a stack of books, it just shears it like that. That is the result of applying a shear of factor 2 to that particular rectangle on the plane. And to practice writing the matrix representation of this, remember, we look at what it does to fundamental points. Here's the point 1, 0. Here's the point 0, 1. You ask, what does it do to individual points? So the shear with factor 2, I'll do the scale factor 2 here, is, first column is what it does to this point here. It has height 0, so it shifts by twice 0, not at all. That stays as 1, 0. This point here has height 1, it'll shift double that, 2 places to the right. 1, 2 to this point here, which has coordinates what are 2, 1, 2, 1. So there is the matrix representation of this shear. And if you change the scale factor to some other number, k, turns out you can check the only number that changes that matrix representation is that number there. So that's the matrix representation we had before. There is the geometric effect of a shear on graph paper. Now I think we can start answering those textbook questions about graphing the effects of shears. All right, so let me do one final more complicated, all-rounded example that takes all 5 ideas together into one typical curriculum type problem just for practice, because I think we're doing very well right now. So let me clean the board yet again, and I'll be back in just a moment. Okay, here's a final practice question going through most everything. Okay, example. Draw the image of A. Okay, so here's a picture of a graph. There's A. It's this little square. I guess it's in like a 1, 2, 3 units up and 2 units up. That square is A, shaded in. Draw the image of A under a translation given by -1, -3. Okay, can we figure out what that means? Can we make an intelligent guess about what that means? And then draw the image of A under the transformation given by this matrix with a 1 and a 0 and a 0 and a -1 in it. So draw where the image of A is when you translate it by this, and then draw the image when you apply that matrix to it. Part B. Name a single transformation that maps A onto B. So where's B? B is a little square over here. So here's A. Can we name a single transformation, so it's in the list of like translation, rotation, reflection, dilation / enlargement, or shear, that takes A onto that? All right? And then part C is write a matrix that represents a transformation that takes A onto this square over here, C. All right, so that's a typical textbook type question on these ideas with graph paper. Do you want to give it a try first before I go through my answers to these? That sounds like a good idea. So try it first, pause the video, and I'll be back in a moment. Okay, so here's my brain on this typical textbook question. Square A. First of all, draw the image of A under the translation given by -1, -3. All right, so in the video we did talk about it's weird to write points as columns, but there's a reason for it. So this is really shift, first of all, -1 in the x direction and -3 in the y direction. So actually I can see what to do. So I have to take this square and translate it, -1 in the x direction, whoop, and -3 in the y direction. So we're going 3 up, we go 3 down. 1, 2, 3. Got that? So -1 left, jump, -3 down, 1, 2, 3 down, gets me here. I believe this is the answer to part A1. There is the image under a translation, 1 unit to left, 3 units down. Great. Now let's draw the image of A under the transformation given by 1, 0 and 0, -1. Okay, first I want to ask, what transformation is given by that matrix? Now, maybe memorize these things. I don't. I'm going to figure it out. This tells me the fundamental point 1, 0 is going to 1, 0. So this matrix doesn't change this fundamental point. It stays as it is. Okay, that point stays as it is. And it takes the other fundamental point 0, 1 to 0, -1. So it takes this point up here and brings it down here. Oh, so it leaves this point the same and it brings upper points downwards. This must be a reflection about the horizontal line. And if I remember some theory that I was doing in the various videos, yes, that's right, that is a reflection about the horizontal line. So the image under the transformation given by B, this matrix here, is just a reflection of this about the horizontal line. So now the image is this one. There it is, bingo. That's the image of A under that matrix transformation. Great, so far so good. Did we get the same things? I hope so. All right, part B. Name a single transformation. I give a single name. Say the word shear, say the word reflection, say the word rotation that takes this thing to that thing. All right, well obviously something's going on because the size is changing. So the one that changes size is dilations, enlargements. So this must be an enlargement. It's kind of weird though because it's actually going in the opposite direction. And you remember it must be an enlargement by some negative number then. So what negative number is it? All right, so it looks like this point, I'll go with this corner here, if it's currently is that distance away from the origin, must have moved opposite direction. Oh, it looks like half the distance. Oh, this one here is that distance from the origin must have moved to the opposite direction that way, which looks like half the distance. I bet it's a dilation with scale factor -1/2, or an enlargement with scale factor -1/2. So my answer is, here's where I'm going to write my answer. Okay, my board technique is terrible, but I'll say enlargement with factor -1/2. That's my answer. All right, how are we doing? 2 done out of 3, 1 more to go. Write a matrix that represents a transformation that takes A, that little square there, to C. Okay, how am I going to do that? How am I going to do that? Well, clearly I could actually just translate it. I could translate it -1 left and 1 unit up. So it could be a translation, -1, 1. But if you recall, it's impossible to represent translations by matrices. So it's not going to be translation because I said it wants a matrix. So I can't use translation. What else could I do to get A to C? Well, another thing could be, actually, if you think about it, I can kind of see if I did this diagonal line, I can see that I could map A to C with a reflection about that diagonal line. Now the trouble is I don't remember what matrix represents that diagonal reflection. I know I talked about it, I know I did in the video, but I don't have it in my head, so I've got to figure it out quickly. What matrix takes this A to C by reflection about the diagonal, well, ask what does it do to the fundamental points. I want the point, okay, here's the matrix, I'll just write it down. I want the point 0, 1 to go over, if I flip diagonally, to, 1, 0 to go to 0, 1. 0, 1. I want the point 0, 1 to go over here to 1, 0. That's it. That must be the matrix that corresponds to the diagonal reflection, and it kind of rings a bell. I think it's what I said in the last lecture, so actually that must be correct. So there it is. That's the typical work that appears in curriculum textbook examples about how to represent these things graphically, doing the interplay of the geometry and the matrix work. So there it is all together. All is grand. This is looking good. So I'm so glad I did this bonus video because I think it actually might help some degree. All right, have fun with it all.